Hello, this is Group 4 of Electronic Digital System, Section 13. This is our project about combinational logic circuit design. We designed a combinational logic circuit that represents a simplified traffic light control system at a junction. We have two logic circuits, one for the basic gates and another one for NAND-NAND network. For the basic circuit, we have three inputs, input A, input B, and input C. Input A, we have a vehicle sensor. Input A represents the presence of vehicles waiting at the traffic light. It gives logic 1 if vehicles are detected and logic 0 if vehicles are not detected. Input B is a pedestrian button. Input B represents the state of the pedestrian button by the road. It gives logic 1 if the pedestrian button is pressed by the pedestrians, and 0 if it's not pressed. Input C is a rush hour indicator. Input C indicates whether it is rush hour or period of high traffic volume. It gives logic 1 for rush hour and logic 0 for normal hours. There are two outputs, output X and output Y. Output X is a traffic light. Output X controls the traffic light for the road junction. If there are vehicles detected and the pedestrian button is not pressed, or during rush hours, the traffic light will give a green light to proceed. If not, the traffic light will give red light. Output Y is a pedestrian walk signal. Output Y controls the pedestrian walk signal. If there is a pedestrian request to cross the road and no vehicles detected, or during normal hours, the pedestrian walk signal is activated, allowing pedestrians to cross the road safely. We will now describe the basic gate logic circuit. For input B enters the NOT gate and it will produce an output of B bar. Then the OR gate will receive input of B bar and C and generate an output of B bar plus C. For the last AND gate, it will receive an input of A and C plus B bar. The final minimum expression for output X is A bracket B bar plus C. For the output Y, firstly an input C will enter a NOT gate and produce a C bar as an output. Then the AND gate will receive B and C bar as input to generate an output of B, C bar. Input A will go through a NOT gate and give a A bar and also a B, C bar as the input for the OR gate. Hence, the minimum expression for output Y will be A bar plus B, C bar. We use the De Morgan's theorem to modify the Boolean equation of basic gates to NAND-NAND network, which use NAND and NOT gates. Input B goes through a NOT gate and becomes B bar. Then A and B bar enter the NAND gate and become A B bar bar. Then A and C enter another NAND gate and become A C bar. Then A B bar bar and A C bar enter the last NAND gate and produce an output of A bracket B bar plus C, which is the same as the output X for the basic gate circuit. Input C enters a NOT gate and becomes C bar. Then B and C bar enter a NAND gate and become B C bar bar. Then A and B C bar bar enter another NAND gate and produce output of A bar plus B C bar, which also is the same as output Y for the basic gate circuit. We will now simulate the waveform for the basic logic circuit. You can see that the result of the waveform is the same to the truth table. For example, an input of 0, 0, and 0 will produce an output X of 0 and output Y of 1. The waveform of the basic logic gate is similar to the waveform of the NAND-NAND logic gate. This shows that our design is successful for the adaptive traffic light system. Thank you.